Okay, so we're to the part of the note packet that's the Geometry Sketchpad investigation, but instead of doing that, what we're going to do is go look at a couple of these applets in Geometry Sketchpad, and then we'll come back to Theorem 10.4. So going to look, first of all, at diameters and chords GeoGebra applet. Okay, so how do diameters and chords play out? And it says you can kind of drag these different dots around and see what happens. So we drag the white one, just makes it bigger and smaller. The purple ones just move around the circle, and looks like the center can also make it bigger and smaller. So when we slide this, it draws a chord on the circle, and then they draw a diameter. We know it's a diameter because it's two of the radii that are congruent. And when they draw it, they have this pink angle marked, and they show that they're bisecting the chord. Let's see what else it shows. Oh, it shows that the pink angle on the other side is the same amount, and we know if two angles are the same amount, if that angle is bisected, and they have to add up to 180 if they're a linear pair and they're congruent, both those angles have to be 90. And then they show the other side of that chord is equivalent and that the arc is also bisected. So some of the questions it asks, what does the movement of the pink angle imply about the intersection? It's bisecting that angle. In essence, the action you observe from the pink angle implies that the diameter and its chord are perpendicular because they form that 90-degree angle. If a diameter intersects a chord in a manner you described in your response 2, if it's perpendicular, what does the diameter do to that chord? It bisects it. And then number 4, it also bisects the arc. So basically it's kind of saying the same thing we said before in theorem. Come on, OneNote. In this theorem here, we're just saying the exact same thing, only backwards. Before we said if a diameter is perpendicular to a chord, then it bisects the chord in its arc. We can also say vice versa. If a segment bisects the chord and it also bisects the arc, and it's perpendicular to those two, to the chord anyway, then it will have to be not just any old line, but a diameter. Let's go look real quick at the other applet. Oh wait, we're not ready for that one, just kidding. Okay, so let's go fill out Theorem 10.4. Oh, we were ready for that one. Sorry guys. So let's look at equidistant chord action in GeoGebra applet. Okay, so that's over here. Recall what you've just discovered. How does this action seen in this applet relate to the action in the previous applet? All right, so it looks like white makes the circle bigger or smaller. This one kind of moves it around, but also makes it bigger and smaller. And then pink, we can just move around the circle. All right, so let's see what happens in this one. First of all, the blue slider for now doesn't change anything. Looks like they're drawing two chords. And that dash line makes me think that this is like a mirror image of this one over here. Okay, so if you want, you can play with this again, but what they're trying to show you is that if these two chords, this dashed line over here and this red chord over here, notice that they have tick marks on these lines coming from the center. They are the same distance away from the center. Then they're going to have to cut off equal amounts of the circle. If it's really short right here, then you're going to have a really long chord. If it's longer, you're going to have a really short chord. But if they're the same distance, you're going to have equivalent chords. And that is our next theorem. In a circle or congruent circles, two chords are congruent if and only if they are equidistant from the center. So just to be sure that we all understand what we're looking at in this picture, yes, these are partial radii. And, if you were to extend it all the way out, it would be a radius. But what they're really trying to show is this same distance from K, the center, to each of these green lines, these chords, is the same. I know it's not drawn to scale, and therefore the chords have to be the same length. So remember, equidistance, distance is not shown doing that, right? Remember, the reason that we have these boxes on here is to show that they are the perpendicular distance, the shortest distance from point K to that line. Okay, so here we are in example 4. Find the value of the variable. So what we see is here's the center of the circle, and y and 3, those have tick marks on it. So y is obviously 3. And then because these are the same distance away from the center, the chords will be equivalent as well. So x is 20. Same idea in part B. This time, instead of showing us that the two chords are equidistant from the center, they start with the fact that the two chords are congruent. So that's supposed to be a W. So W equals 10. And we know that because they both have tick marks on them. And therefore, because they're the same distance, because they're the same length, they would have to be the same distance from the center. These will have to be congruent as well. All right, so you try. Okay, so I said x is 5 and y is 15. We knew that because they were the same distance away from the center. We had tick marks on both of these, that those were both 5. Therefore, the chords had to be the same length. All right, and so I think I'll do the next part in the next video.